So we're looking at curve sketching with the second derivative right now. So if you've done the preamble, you know that if the second derivative is positive, the function is concave up. If the second derivative is negative, the function is concave down. At an inflection point where it changes concavity from down to up or vice versa, the second derivative will be equal to 0. Now we have a couple of nuances that we need to consider. First is this function is an example. So f at x is x to the exponent 4. And as you can see, the slope is increasing as we go from left to right. And so that means, and it's doing it everywhere in that function. That means the second derivative is positive everywhere in that function. So this is concave up everywhere. Second derivative of f at x equals x to the 4th is 12x squared. The second derivative is 0 when x is 0. But there's no change in concavity at 0. So there's this tricky thing. If the second derivative is equal to 0, that does not necessarily imply a point of inflection. And so when you are trying to find points of inflection, you need to check either side to check to make sure the second derivative has changed sign. So there's that bit of trickiness. Here's another example of some trickiness. This is f at x equals x to the exponent 2/3. And so there you can see it's this cuspy type thing. And as I go from left to right here, the slope is decreasing. And suddenly it switches. It actually goes through 0. And then suddenly the slope is, the slope is actually increasing as we go through here. And then it's decreasing as we go through here. So this is concave up. Concave. Yeah, this is concave down. And this is also concave down. Okay. If you take the second derivative, you'll actually notice it's negative 2/9 times 1 over x to the exponent 4/9. The second derivative does not exist when x is equal to 0. Okay, now this isn't actually changed. This is concave down and this is concave down, but there is no inflection point here. Okay, so you have to be careful. And our example function, there's no inflection point and it actually changes concavity. All right, okay, so I've got 3 functions. We're just going to quickly go over the second derivative with and how you sketch them. The first one is a cubic function, and pretty easy to take the derivative. We just use the power rule. We take the derivative again using the power rule, and we end up with the second derivative is equal to 6x minus 6. We can common factor that, and we end up with 6 times x minus 1. All right, so something exciting is going to happen when x is equal to 1. So the second derivative when x is equal to 1 is equal to 0. And so we'll just make a little interval table here. So when x is equal to 1, something exciting happens. So let's look at the situation where x is less than 1 and the situation where x is greater than 1. And we'll just look at the value of the second derivative. We'll check that sign, and then we'll come to a conclusion about whether it's concave up or concave down. And so when x is less than 1, say for example 0, 0 minus 1 is negative 1, times 6 is negative 6. And so in this area, the second derivative is negative. And so I'm going to conclude that it's concave down. Down with concaves. Okay. What about when x is greater than 0, or sorry, greater than 1? So for example, 2, I could put in a test value of 2. 2 minus 1 is 1. 6 times 1 is 6, which is positive. Second derivative is positive. Concave up. All right. If we were sketching that function, we probably would have gone through looking at the function, figure out where it's positive, negative, x and y intercepts, looked at the first derivative, found out where it's increasing or decreasing, and then we'd figure out if it's concave up or concave down, or we have figured out it's concave down when x is less than 1, and it's concave up when x is greater than 1. That one is straightforward. There are no weird discontinuities in that function. Let's go to this function. So this is one of those peculiar functions that we were talking about before. And, oh yes, here we go. So x, this is x to the exponent 1/3. G primed at x is just using the power rule 1/3 times x to the negative 2/3. Use the power rule again, and we wind up with the derivative, the second derivative, negative 2/9 x to the exponent 5/3. Okay, so G double primed at 0 is when something happens, and in this case, it's undefined. So there is no inflection point technically in this case. And if you actually looked at this function, you'd see it has this kind of a neat appearance. It's a cubic function sort of turned on its side, and it goes like this. I should make this steeper. And right there it has a tangent with an undefined slope. Okay, so in spite of that inflection point not existing, I know there's something exciting probably happens there. And so our point where exciting stuff happens is when x is equal to 0. And so we want to look at the case where x is less than 0, and we want to look at the case where x is greater than 0, and we want to examine the sign as we go through there. All right, if x is less than 0, so like -1, -1 to the exponent 5 is -1, and the cube root of -1 is -1 times -2/9 is positive. And so in this region, when x is less than 0, second derivative is positive. I could go through the same exercise here. However, second derivative is negative. And so I would conclude that it's concave up when x is less than 0, and it's concave down when x is greater than 0. And so I can just algebraically see what happens with this interesting function. Okay. Last one. So this is a rational function. It's one of these ones where it does weird stuff as you take the derivative and then take the second derivative. There are common factors in the top and bottom. They cancel out. We end up with x squared plus 3 to the exponent 3, not 4, on the bottom. And the top is 6x squared minus 6. And we can common factor out a 6 out of the top. And now we need to look at the second derivative and decide what to do. So second derivative is going to be equal to 0. Fortunately, when the top is equal to 0, which is when x squared minus 1 is equal to 0. So when x is equal to 1, or when x is equal to -1, second derivative is equal to 0. So this is a case where we wind up with two intervals where we need to be checking our concavity. Fortunately, there's no discontinuity on the bottom. So it's continuous everywhere. We don't have any weirdness going on in terms of an undefined point. All right. So exciting things happen when x is equal to -1 and when x is equal to 1. And so when x is less than -1, something's going to be happening. When x is between -1 and 1, there might be something different. And when x is greater than 1, there might be something different again. So here we go. Interval table galore. Okay. So let's figure out what the sign of the second derivative is. Yeah, this is fine. Okay. So sign of the second derivative when x is less than -1. say, for example, 2. 4 minus 1 is 3, so that's positive. Multiply it by a positive, divide it by a positive. This whole thing is positive. I like that. Okay. When x is between -1 and 1, I'm going to pick a test value of 0 because it's easy. 0 minus 1 is negative. Negative times a positive is a positive, divided by a positive is a... Oh, negative times a positive is actually... Am I right? Is it a negative? Yes, it is. Okay, divided by a positive, the negative. And when x is greater than 1, I can pick whatever I like, but this is going to be positive as well. And so it's concave up, concave down in this area between -1 and 1, and it's concave. I guess I should write down just to be thorough. Concave up. And so there we go. We've used the second derivative, and we can tell what's going on with this function. And this one actually is quite interesting to look at. So take a look at it on the course page. But it does this sort of a... So there's our inflection point. So it does this sort of a concave up until we get to -1, and then suddenly it switches to concave down until we get to +1, and then it switches back to concave up. And so that's sort of what that function looks like. Okay, good. So there we go. Curve sketching in the second derivative tells us concavity. There's also this thing called the second derivative test, which lets you know if you've got a maximum or a minimum at a turning point. Okay, so you can see that this is concave down at this turning point. So if we were doing the first derivative, we'd locate the turning point. If it's concave down there, that means it's a local maximum. If it was concave up here, that would mean it's a local minimum. So there's also a second derivative test that we get doing when we start doing optimization. And that's the second derivative.